Hi, welcome to Notes 34. Couple of points I want to bring up before you start watching this. Number one, use your pause key when you're watching this. You're welcome to pause and rewind something if you don't understand. You can't just watch it all the way through sometimes. Second thing, you might still have questions after watching this. You can email me with your questions and I'll try to get back to you as soon as possible, or you can bring them to class. Remember, we have that whole class hour where we can ask questions and talk. So good luck, and I'll see you tomorrow. Before we start, I want to talk quick about the difference between these functions and these functions. These functions have exponents in them, but they're not exponential. This is a quadratic function because it has x squared. This is a cubic function because it has x cubed. In order for it to be exponential, there has to be the x in the exponent. We're going to talk today about logarithms, intro to logarithms. We're going to touch on a few different things. First off, why do you even need logs? What are they mathematically? Sometimes I think we jump into the rules about logarithms and we don't really talk about why they're needed. So what's the use of logarithms? Second thing, we're going to talk about notation, how you write logs. Then we're going to talk about how to change forms. And last, we'll talk about how to evaluate logarithms. We have a lot to do today. So the first thing is, what is a log? Why do we need it? And if you think about all through algebra, what we've talked about so far, how you solve equations. If you have an addition, how do you undo that? Well, you do the opposite. You subtract. If you have a multiply, how do you undo that? You divide, the opposite operation. If you have something squared, how do you undo that? The opposite of it, you square root. Yesterday we talked about exponential equations. And what logs are is they are the undoer of exponential equations. So before we get into logs, let's just talk about this situation right here. A bacteria has a colony that originally had 1,000 bacteria. So at time of 0, there was 1,000 bacteria. And each hour, it doubled in size. So after 1 hour, there were 2,000, doubles to 4,000, doubles to 8,000. So how many bacteria would there be after 4 hours? Well, we can see by looking at our chart that if we just extend our time 1 more hour, it will double again. So there will be 16,000 bacteria. How about after 10 hours? There's a couple of ways we could do this. We could just keep multiplying by 2 until we got to a time of 10 hours, or we could just use our equation. If we put 10 in for the t, and then use our calculator, 1,000 times 2 to the 10th, we'll get 1,024,000 bacteria. Okay, no need for logs yet. But now let's say that we get this question. When will the number of bacteria be 32,000? Well, if we think about this, we can actually answer this question kind of by our chart. What will happen during the next hour, in hour 5? Well, our bacteria is going to double again and we'll get 32,000. So when time is 5, we'll have 32,000 bacteria. Well, how about 50? If you continue your chart out, the next one would be 64,000. So you know it's going to be somewhere in between 5 and 6. We don't really know where. How can we solve for that exactly? Let's go back to our equation. We know that this equals the amount of bacteria. So if we set that equal to 50,000, we'll have this equation. 50,000 equals 1,000 times 2 to the t. And we'll try to solve for t. So first we can divide both sides by 1,000. So we get 50 equals 2 to the t. We need a way to get that t out of the exponent, to solve for that t. There's nothing right now that undoes an exponential function, and that's what logs do. This is the need for logarithms right here, is to answer questions like this in a word problem. Here is the notation for logarithms. Log base b of x is equal to y, and that is equivalent to b to the y equals x. And we use this when we're talking about logs. We a lot of times will change forms. We'll talk about that next in the next little section. Right now we're just going to kind of talk about notation and some things on your calculator, some log shorthand. If you look on your calculator, you don't have a base button. There's no little B button there. It just says log. If you look on your calculator, we use 2 logs most commonly, and one is base 10 and one is base e. Log base 10 is so common that they just use log of x to mean log base 10. So whenever you see just log of x, it means log base 10. This right here stands for natural log. LN stands for natural log. Yeah. What that means is log base e. It's the undoer of e to the x. So natural log undoes e to the x. Natural log means log base e. These are both very easy to do on our calculator. Whenever you have log of 3, remember that means log base 10 of 3. And you can just punch that into your calculator. Log of 3, and it'll give you a big long decimal number that you can round. Same thing for natural log. Remember, this means log base e of 7. So you just type in your calculator ln 7, and you'll get a decimal. That you can write down. The first skill that we're going to learn with logs is actually changing forms between logarithmic form and exponential form. Why? Why would we do this? It helps us understand the relationships between exponential and logarithmic. It can also help us when we're solving equations, and it can also help us sometimes to evaluate logs. So what I do is I memorize a template form of it. I use this one. I remember that 10 to the third is 1,000, right? 10 times 10 times 10 makes 1,000. And that goes with log base 10 of 1,000 is 3. And I can check that one easily on my calculator. I can type in log base, just log of 1,000, and check that that's 3. So I know that these go together, and that helps me match up my pieces. So if I have log base 2 of 16 equals 4, and I'm trying to change forms, I know that the 10 goes here, so that means that the 2 goes here, and the next number would be where the 3 is. Well, the 3 is on the other side of the equal sign, so I take the 4. So 2 to the 4th equals, and then I want the 1,000, and the 1,000 is in the spot where the 16 is. So 2 to the 4th equals 16. Also, it's kind of, the visual kind of helps me. 2 to the 4th equals 16. Boom, boom, boom. So then once I have 1, it's easier for me to change. 2/3 to the 2nd power equals 4/9. Ten to the -1 power equals 0.1. Now this one has no base. Remember, when there's no base, that actually implies a base of 10. So this is 10 to the 2nd power equals 100. Okay, natural log. Remember that natural log is the same thing as log base e. So this is actually saying that e to the second power equals, well, e to the second power. If I'm trying to change from exponential to logarithmic form, again, I use my template function here, which actually is right here. 10 to the third is 1,000. I know that 10 to the third is 1,000 is the same thing as log base 10 of 1,000 is 3. Now, technically, I wouldn't have even needed to write that 10. I could have just written log of 1,000 is 3 because if there's no base, 10 is implied. So now I say, okay, I know that to change forms, I'm going to have log base what? Well, the 10 is the base, so I see where that is in my template function, right here. So that means that the 3 is the base. And then I want the 1,000, okay, over here, that's the thing it was equal to, so that means the 81. So log base 3 of 81 equals 4. 3 to the 4th is 81. So this one is log base 10. The negative 2 goes over here, 0.01. 10 to the negative 2 equals 0.01. Log base 5. 2 goes over here, 25. Again, I check it. 5 to the second power equals 25. 10 to the third is 1,000. Now this one gets kind of tricky here. Let's see. Log base e, and then of the 1 is e. E to the first equals e. And that's how you change forms.